In this video of the fundamentals of electrical circuit series, what we're going to focus on is circuits that have resistors and inductor or resistors and capacitors in them. And the reason we do that to simplify the equations we have to solve. If we just have we have inductors and resistors only, then we'll end up with a first order differential equation, meaning that first order derivatives would be present in our equations. If we have a C and R together, C, R, and L all together, then instead of first order, we'll end up with second order, which we're going to treat that in our later videos. But for now, we're going to limit our case to just having a resistor and an inductor in circuit, or having resistors and capacitors in circuit. They don't have to be one capacitor or one resistor, but they got to be only resistors and capacitors in one circuit, or is resistors and inductors in another circuit. Okay, then we'll end up with the first order differential equation, or first order derivatives in our equation, if you want to think about it. So what we're doing in this video is, before we get down to doing some work to derive the process, is we need to understand what is the life cycle of a circuit. What does that mean? It means when you have a circuit, what are the different what are the different events that could happen? And actually, in a circuit, it's relatively straightforward. For most circuit, you either turned it on, on position, if you want to think about it. Then after a while, it stabilizes, and then it starts running in a steady state. Okay, and then at some point you're going to shut it off, and then that's this back end, and then after a while all the power goes out, and the thing just stops working and quiets down. No electricity gets dissipated and all that kind of stuff. So during the phase where we are applying the power, so that would be kind of what, if you want to think about it, is that is referred to as a step response. And that is actually the focus of this video. This video is going to focus on how do we figure out what the step response, which means what is the voltage and current when power is applied to it. So step response is a case where you end up having a power source left in your circuit. And then at later times, we'll take a look at, we'll look at natural response, not in this video, but in future videos, where, okay, now I've shut the power off, because all the dependent sources have been turned off. What is going to happen to my circuit? What is going to happen to current and voltages in my circuit, and how do I go about analyzing it? And then as even further in the future videos, we're going to start focusing on, okay, now I've turned my circuit on, is stabilized, and is operating. Actually, in many cases, the steady state, that's the case where we're most interested in. But first, we got to start with the step response. We just and we want to know kind of what happens. All right, so let's take a look at it down here, and I'm going to do these. I have these two cases more or less side by side, so you can kind of watch it develop. In this side we've got a capacitor, so that's really important to know. So in this side we've got an RC circuit, and also want to draw your attention to something interesting here. If you carefully look at it, you will see that this piece of the circuit is simply a Norton equivalent. So when we are actually solving this problem, a lot of cases we will try to reduce the rest of the circuit other than the capacitor into a Norton equivalent and plug it in here, so we can take advantage of the equations that we have derived here. Now, as you all noticed also, is that this circuit has two life. It has life before time equal to 0 and has life after time equal to 0. And if you noticed, before time equal to 0, the switch was open, so the current would just flow through the resistor. And then at time t equals 0 is closed. Now you got a circuit which has got a capacitor in it too. So since this circuit, after the time we are interested in analyzing it, we are interested in analyzing the step response after time zero. So that means after time zero, when that switch is closed, now we got a source in here, therefore is a step response. That's how you know you got a step response to evaluate. Now, based on everything we've learned so far, this is a simple, let me choose a different color. This is a simple KCL. You could do it by KVL, but we did it KCL. So if you do a node here, you do a reference node in here, you will find that, okay, you're going to have this is minus IS, right? So the current leaving this node is minus IS. The current coming down here is whatever this voltage is, voltage divided by resistor. And then the current coming down here is C dV dt. So if I sum all of these together, I've got an equation that looks like this. C dV dt for the current here, V over R for current here, and since this was a minus IS went to the other side. Pretty straightforward. At this point, this is the process of finding V of t, which is the only variable in here. If you look at it, IS is a constant current, V is variable, so you got a V by itself, and then you got a derivative of V. Again, we're not going to take the time here to go through how you walk through the first order differential equation to get the answer, nonetheless to say that this is the answer. So this isn't, so anytime you can get your circuit to look like that, you can use V of t equal to ISR to solve the problem. Now, if you come down here, we'll start plotting. Let's go ahead and plot V of t. If you plot V of t for this, we will see that as the time goes by, the V of t will start at 0, and then assuming the initial condition is 0, so and it grows to so we are assuming the initial, if the initial condition was higher, we'll start at a higher level. So now what we got is this thing goes up, and if you notice as it goes up, it goes up by basically e to the 1 when t is equal to tau, and tau is RC. This is an important concept. This is called the time constant. So when we are here, we've got 1 over t. When you get over here, 1 over e to the power of 2, and then when you get here, you're almost there. This is, so usually this this curve it's by the time you get to 3 time constant, most of the time we assume you have basically stabilized because it's so close to the final value that will say stabilized. Now I of t, okay, is C dV dt, and if you look at it, I in this particular capacitors, when you throw the switch, I is short, all of IS goes through here because capacitor is short, and as the time goes by, that capacitor opens up and it goes down to, again, when once you get to about 3 time constant, you can assume you are almost stabilized at 0, even though it theoretically never reaches 0. Okay, so now let's go ahead and take a look at the inductor. The inductor is very similar to the capacitors if you look at it in this case. So this is the RL circuit, and if you look at it, if you really pay attention, you see that the circuit that is feeding this is basically a Thevenin equivalent. Okay, and then so if we were able to get our circuit to look like a Thevenin equivalent, we'll be all set. And then if you look over here at the time t equals 0, the switch closes. So the inductor had nothing in it for a while, so I's initial condition is 0 in this case. But then as soon as we close the circuit, then this voltage appears here. And we know from our conversations before is that inductors, when you put it, they act like an open, and over time, when things stabilize, they become a short. And that's really driven by the equation that the voltage is equal to L di dt, right? So anyway, so that's where that comes from. Now, in this particular case, it looked like we used the mesh to write the equation. So minus Vs plus Ri plus L di dt. And if you look at this equation, even though it's a little bit of a different structure than the C, more or less it looks similar. You got I, which is the variable. You've got a di dt, which is the first derivative of it. So therefore, this is a first order differential equation, and the answer is very similar. Again, if you look at it with different variables, but very similar for when t is larger than 0. So if you look at the curves, you'll see that in this case, the I behave like what the voltage was behaving as C, and V behave as that. And V behave in inductors behave much like I behaved is in capacitors. The one thing to remember when you look at these things, your time constant is L over R. So that's what tells you, okay, when I get to 3t, things have stabilized here, 3 tau stabilized here, and that is called the time constant. Okay, so now if you want to solve these, first thing I got to do, I got to find the initial condition, whatever the initial condition is before the switch is closed. This indicates switch closes at t equal to 0. Then if I'm doing the RC circuit, I got to find the Norton equivalent. So if you're solving this problem, step 1 is you need to find out before t, just about is equal to wherever you're throwing the switch. In this case is 0, and just a little bit before that time you want to find initial condition. And step 2 is you want to determine if you got a step response or a natural response. So you in here you figure out, okay, do I have a source in my system? If I have a source after the switch is thrown, then I have a step response. In this particular case, both of you have a step response, and that's great. So that's step 2, and therefore that means I can use this equation or this equation. So once you determine step response, then step 3 is you find either Norton for RL, you find the Norton equivalent, RL, you find the Thevenin equivalent, because you want to make it look like this, right? And then, or for RC, you find a Norton equivalent. Okay. Once I have that, then just plug the values from your circuit into appropriate equation, into either a RL or RC equation. And you're done. Okay. So again, 3 steps, and let's go ahead and take a minute and see if we can do an example real quick for something like this, and go there. So let's say somebody gives you a circuit which looks like you've got a source, you've got a resistance 5 kilo ohm, 20 volts, and 10 kilo ohms, and you got a switch, and switch is closing at t equal to 0, so that's the time. And then I have an inductor, and there we have it. So what did we say the first step was? The first step was just before the switch is closed, find the initial condition. In this case, I have my initial, so step 1 is before switch is closed, find IL, let's call this one IL, at time 0. That's when the switch is closed. So we got to be a little bit careful. So when the switch, because the switch has been open for a while, and they usually say for a switch has been open for a long time, that means the inductor really hasn't had any current. So in this case, we can just simply say IL of 0 is equal to 0 amp and be done with it. So the next step here would be, let's go ahead and do the circuitry is this a step response? It's a natural response. We say, okay, when you close the circuit, then you're going to have a source in the circuit. So since there is a source, since there is an independent source, after t larger than t equal to 0, which is the switch is closed, then you have a step response. Okay, so that's great. So I have a step response. I've got an inductor. So what I really would like to do is if I could turn this from here to here into a Thevenin equivalent, I'll be great. So in this case, I need to find Thevenin equivalent with respect to inductor terminals. Okay. So what I'll do is I'll go ahead and redraw this circuit. So I'll have 20 volts. I have a resistor here, and all I'm trying to do is find the Thevenin equivalent with respect to this 10K, 5K. This is a rather simple circuit, so I can just take a look at this and say, look, I can take the shortcut for our Thevenin and just basically deactivate the 20 volt. If I deactivate the 20 volt, I'm going to have the 5K and 10K in parallel, so that's all I have to do. 5 in parallel with 10, and it's 3.3 kilo ohms. Great. And then V open circuit, step 2 is V open circuit with respect to here and here, which is where the inductors are. If I look at it, it's 20 volts kind of across the voltage divider across this. So if this is A, this is B, the voltage across here is open, it's going to be basically 20 volts times 10 divided by the total resistance, which is 5 plus 10, or 13.3 volts. So now I got V Thevenin. So now my circuit is, I can redraw step 4. If you go up here, your step 4 is to plug the values in and figure out what RL is. So if I go over here, I will find that, okay, I've got step 4, I've got the Thevenin equivalent, which is 13.3 volts. I've got R Thevenin, which is 3.3K, and then I've got my inductors in here. And earlier I figured out that I at times 0, IL at times 0, the initial condition was 0. Now I can go up here and literally take this piece of this equation and plug in my values into it. Vs is basically the V Thevenin, R I have, and all that. So I just simply have to plug it into that equation and I'll be done. So let's go do that real quick here. So all I have to do is say, okay, my V, let's say they were asking for I, just to make life simpler. So IL time T is equal to Vs, which is now 13.3 divided by R, which is 3.3, plus initial condition, which was 0 in our case, minus Vs over R, e to the minus R over L. I'm just writing that equation for this, and this is for t larger than or equal to 0. So if I do that, then I have IL of t equals to, basically when you clean everything up, you'll end up with 4 minus 4 e to the minus 8250 t amps. If somebody wants the voltage across the inductor, that would be basically L di dt. So the voltage, if you need the voltage, is going to be L di dt. So now we found a response of what the voltage and current of the inductor is for a step response, RL or RC step response. And again, the steps are pretty straightforward. Figure out what happened just before the switch, find the initial condition, determine if you got a step response, and the only thing you need to do is figure out if there is a source in your circuit, then you have a step response after the switch is closed. Then if you're doing an RC, you find a Norton. If you're doing an RL, you find a Thevenin. And then once you've cleaned it up and have the circuit, then you will have the values that you need to use for RC to use these equations, and for RL to use these equations. That brings us to the end of the step response for RL and RC circuit.